So we're moving topics a bit today. Before that, any questions or comments about the things we've been discussing? Okay. So let's continue with our discussion today. Okay. So what we're trying to do is to move to a discussion of the propagation of strings in space. Okay. Today's lecture, and probably the next one, will deal with material given in Brzezinski's book. And then after that, we'll spend maybe a lecture and a half describing more systematic applications. Random scheme, Brzezinski's. Alright. So, but let me start approaching the topic like Brzezinski does. So, when we first started discussing the motion of strings in flat space, we wrote down this Polyakov action to describe the motion of strings. And in much of today's lecture, we continue talking about strings in flat space, but revisit the question of vertex operators. If you remember the logic of the courses we presented and so far, we went to conformal gauge. Okay? And then we sat in conformal gauge and then said that conformal primaries were good vertex operators, or more sophisticatedly, BRST invariant operators were good vertex operators, and because they gave us well-behaved sensible results and so on. Okay. Now, we could have instead addressed the question of what are the good vertex operators in the theory in Polyakov's language. Namely, in the language of integrating both over the coordinates that describe the motion of the worldsheet, as well as the worldsheet metric. We could, in that language, have already started addressing the question: what insertions can we add to this string path integral? Without first sort of we could have tried to do a systematic analysis of this question of insertions at the beginning stage itself. Okay? We did some of this, but I'm going to present this a little bit. Okay. So the question that we could have asked is the following. Suppose we've got this action which is 1 by 4 pi prime square root G DAB. Still at the moment flat space and still with B equals 0 and so on. We've got this action. And we write down the Polyakov path integral dx dg dg s. What vertex operators are there? What vertex operators are there that we could add to this integral? Okay. Now, the basic guiding principle is always wide operators. Okay? We want this path integral to be wide invariant for all the reasons that we mentioned before. Okay? And so any vertex operators that we of course demand diffeomorphism invariance, worldsheet diffeomorphism invariance from vertex operators. We will also demand that they be wide invariant. Okay? So let's see how we can try to address the questions of what vertex operators could enter our action. What vertex operators will enter our path integral without invoking sophisticated concepts of conformal gauge BRST invariance. Okay. So let's first discuss the tachyon vertex operator. So in addition to this e to the power minus we want to build something that's diffeomorphism invariant and also wide invariant. Okay. So if we want diffeomorphism invariance, we'll integrate this over the worldsheet, and we want to put an e to the pi k dot x. And the question we're going to ask is, where is this insertion wide invariant? Okay. Now, in order to address this question, At first it seems like this insertion must automatically be violent. If you're very naive, you think this insertion is automatically violent, because while transformations appear not to act on X. They appear to act on the world sheet metric, but not on X. So why should there be any transformation of this field as a Y transformation? We know this is not true. We know this is not true because we know that e to the power k dot x has conformal weight. Remember, the conformal transformations are a compounding of a diffeomorphism transformation and a Y transformation. So the fact that this transforms will give the fact that it's a diffeomorphism scalar and that transforms with a certain conformal weight allows us to deduce, a posteriori how it transforms under Y transformation. But we don't want to use all that machine. We just want to try to see if we can directly see how this transforms under Y transformations. Okay? So now, from this point of view, it seems a little positive, right? X is just X. In the path integral, it doesn't seem G changes under Y transformation, but X doesn't change, so why should there be any action on e to the power k dot x? Okay? If there was no action on e to the power k dot x, this could never be violent, right? Because square root G transforms under Y transformations, e to the power k dot x doesn't, so this would never be violent. Okay. Now, the key point, of course, is that insertions inside a path integral involving multiplications of fields at the same point are ill-defined. And they have to be regulated. Okay? So we have to define what we mean by this simplified matrix. If we just mean the insertion of this thing into the path integral, it makes no sense. It's imperative. As always, we have to define what that object means. Okay? And it's in that definition, in specifying a careful definition, in the regulation of the UV, as always, that the Y factor keeps. Okay? So let's see how, let's remind ourselves how we did this on the flat world sheet. Conformity. In conformity in theory of the flat world sheet, what we did was we said that any function of x, the renormalized function, was defined as e to the power factors acting on the same function, the unregulated function x, where this delta of sigma prime is equal to alpha prime by 2 log of sigma prime. Okay? This thing was the negative of the 2-point function. The negative of the 2-point function between x and sigma and x and sigma prime, and we subtracted out all the various weak contractions to define a normal order operator by this operation. Okay? This is so wherever we dealt with e to the power k dot x, it's always a renormalized operator defined by this symbol, by this operation, and that's the object that had good transformation. I mean, it makes sense. You compute its correlation functions. It's also the object that, for which conformal invariance tells us we know how to transform under Y transformations. Okay, so now the question we're going to ask is, of course, this definition is only been given in flat space. Flat world sheet space. Okay? Now we want a definition that is both diffeomorphism, that is a diffeomorphism. Okay? So what we'll do is, as always, we'll take the attribute that we try to make diffeomorphism invariance manifest and then check for it. Okay? So we want to modify this definition somehow to make it diffeomorphism. Right? How do we do it? The question is, what do we replace this delta of sigma prime by? Okay? And there are many things one can do. This never occurred to you Understand? But what we're going to do is what? Okay, what we're going to do is to replace delta of sigma sigma prime by what we call d of sigma. Where d of sigma sigma prime is defined to be the geodesic distance, the proper distance along the geodesic that links the point sigma. Okay? So, given 2 points sigma and sigma prime, our rule is construct the geodesic that goes from sigma to sigma prime. Compute the proper distance between sigma and sigma prime on this geodesic and put that in. And of course we want a square. Is this clear? This clearly reduces to what we did in flat space, in the flat space limit. Again, since it has the same short distance properties, it's going to remove all singularities. Okay? And it's also clearly diffeomorphism. Because d of sigma sigma prime is diffeomorphism. Is this clear? Okay. Yeah. Okay. If you go far enough away, there may be multiple, but we will only have need for this, whether the users will find local operators. So we'll only have need for infinite. Need for infinite and Hamilton's never far away from RP. So, in fact, this geodesic will never be far from this naive straight line. Okay. So this is going to be our definition of this operator. And we're going to try to understand this operator d of sigma sigma prime a little better. But before we do that, let's work with the crudest approximation. You say, when sigma and sigma prime are very near each other, okay, then d of sigma sigma prime, you say, well, we've used diffeomorphism invariance, let's say, to set the worldsheet metric. Now let's use diffeomorphism invariance to set the worldsheet metric to be eta at e to the power 2. Okay? So, d of sigma sigma prime, when sigma and sigma prime are very near to each other, okay, as near as they can get, okay, there's an obvious lowest order approximation to this. And that is simply sigma minus sigma prime, the whole thing squared, times e to the power 2 omega sigma. D squared is this. Is this clear? If basically in any coordinate pattern you go in a straight line, in any coordinate system, in particular the one we draw, you go in a straight line, and this is the factor of the metric that tells you the distance of that straight line. So this approximation, which is valid for sigma and sigma prime are infinitesimally close, okay? The path, the fact that it's a geodesic, we've not taken that into account computing the path. The path is just a straight line in these coordinates. But we take into account finding what the distance of that path is. Of course, now you can ask why use omega of sigma rather than omega of sigma prime. And the answer is that those two differ when you tailor expand at higher order than sigma and sigma. Right, so this answer is only meant to be correct to second order and sigma and sigma prime. If you get corrections that we will study in more detail at higher orders. But before we undertake that technical study of what this object is as we go to higher orders, let's look immediately at what consequences we get from using this approximation, which will turn out to be sufficient for the study of the tangent matrix. Okay? Yeah. So let's. Now this tells us that within this approximation, the log of d squared is simply alpha prime by 2 log of sigma minus sigma prime the whole thing squared plus alpha prime times omega. What's it? Okay? So now let's see how that e to the power I k dot x, the square root g e to the power k dot x insertion changes under a Weyl transformation. You see, all of this part is independent of the Weyl transformation, so we can forget about it. All of the dependence of the operator e to the power k dot x appears from its renormalization, okay, and is in this term. Okay, so let's make an infinitesimal Weyl transformation. Let's make an infinitesimal Weyl transformation into pi k dot x. So e to the pi I k dot x renormalized, which was equal to now we only work with first order and omega. So which was equal to 1 plus half 1 plus half. Now each of these functional derivatives pick up I k. So I k dot and the k dot, so that's then a minus k square. Okay? And then we keep track only of the part of there's all this business. And we only keep track of the part that depends on omega. So we get minus alpha prime k square times omega, acting on e to the pi t prime. Okay, so actually since more precisely what we found is that delta of e to the pi k dot x renormalized is equal to this times delta. That's really what we found. The first one. Let me clear this. Okay? Now, on the other hand, delta of square root g is equal to 2 omega square root g. Okay? So, delta, we get delta of square root g times e to the power k dot x. That object is equal to 2 minus alpha prime k squared by 2 into delta omega times square root g e to the power k dot x. And therefore this is 0. This is 0 if k squared is equal to 4 by alpha prime is equal to 4 by alpha prime, and that's the must. That's the must share condition for that. Is this clear? The basic idea here is very simple. You define your operator in a diffeomorphism invariant way. That will inevitably put the Weyl factor, make your operator depend on the Weyl factor. Because essentially the definition of the operator involves doing a short distance cutoff. Now you want a diffeomorphism invariant short distance cutoff. So that will depend on the method, that will cut it off in proper distance. Proper distance knows about omega. So it will depend on the Weyl factor. Okay? And then you look at how this operator changes as you vary omega, and that gives you the change of the operator and the Weyl factor. Is this clear? Okay. Now, we're now going to repeat this exercise. We're now going to repeat this complicated problem of looking at the massless vertex operators. Okay? And this is a more complicated exercise in several ways. The first of which is that it's going to require us to more accurately compute this. The basic point that we can get away with this crude approximation to the distance, the geodesic distance between 2 points, because the operator that we inserted just had x at the same point. It didn't have derivatives of x at that point. But now, the massless vertex operators have derivatives of x. Okay? So they explore in this formula, this 2-point function formula, this formula which involves subtraction of x at one point and x at another point, they start exploring the two operators going further away. Just in the derivative expansion, of course. Okay? So in order to do the calculation, for the similar calculation for massless vertex operators, we're going to need to more accurately estimate the distance between the geodesic distance between 2 points. Okay, so that's the exercise we're now going to try to undertake. Okay, so the exercise is a trivial one. It's an exercise in solving the geodesic equation in the neighborhood of a point. So we adopt the formula H. So GAB is equal to what do we call it? Delta AB and e to the power 2 theta. Okay? And now we're going to try to try and solve the geodesic equation. So in order to do that, let's find out the gamma simples. Okay. Remember that gamma AB. Well, let me first do this guy with 3 lower indices and then brings 1. So gamma ABC is half of GACB plus GBC A minus GABC. Now, in this particular case, everything takes into work because all derivatives act only on omega. Okay? So every time you have a GAC comma B is simply GAC and 2 del B of omega. That is the derivative factor we get. Okay? So what we get is equal to the halves go away because we get 2's. We have e to the power 2 omega outside, and we get delta AC del B omega plus delta BC del A omega minus delta AB del C. Okay? Now, in order to get gamma AB with the C up, I'm supposed to multiply with an inverse metric. The inverse metric is proportional to delta, but with an e to the power minus 2. Okay? So, gamma ABC is simply just removes this. Is this form without that. Delta AC del B omega plus delta BC del A omega minus delta AB del C. Okay, so this is the exact formula for this guy. Okay. Now we're going to try and solve the equation d2xa by d2 lambda squared plus gamma A bc del xb by del lambda del xc by del lambda is equal to 0. this is the formula. This is the formula. Put any values for A, B, and C in there. Plug it in this here. You can raise, lower, it doesn't matter. All the raising and lowering is with respect to getting. Okay, this is the answer. You put in some value of A, B, C, you plug in here, you get the answer. Okay, great. So now we're going to try to solve this this equation systematically. So what are we going to do? You see, we're going to solve for a geodesic that goes between one point and another, order by order in the distance between the 2 points, in xa minus xb. Okay? Order by order the xa minus xb. Okay? So, how do we do that? So, I can get it using the topic. Okay, good. Okay, good. Okay, see. Now, the first thing we have to understand is why is the lowest order solution here? Why is the lowest order solution going to be the straight line? Okay, so the lowest order solution is going to be the straight line for the following reason. See, suppose we had XA is equal to, suppose we want a geodesic that's going between XA and XB. Okay? So suppose we have, and let's say that this point is 0 and we go to X. XA. So suppose we have X of lambda, and we'll choose a convention so that lambda along our path runs from 0 to 1. Okay? So, suppose we choose XA is equal to lambda, XA of lambda. Let me call this Y notationally. XA of lambda is equal to YA times omega. Okay? XA of lambda is equal to YA times lambda. Suppose I put this in as a trial solution to this equation. Okay. And this term here is going to be 0. This term will not. Okay? However, this term is not 0, but is of order YA squared. order and this distance expansion, when you plug this in the next order, so what we're going to solve this order by order. So we're going to say that xa of lambda is equal to xa0 plus xa1 plus lambda. Okay? Now let me take this as a trial ansatz. So I'm going to suggest that xa of 0 is this object. Notice that xa of 0 is itself linear in y. But the source term that we get for xa1, when we plug in here as a correction, is quadratic in y. Okay? So if we're solving in a power series expansion in y, if we're solving in a power series expansion in powers of y, that is the distance between the points. This is a good zeroth order approximation to us. Is this clear? So now the next question is, what is the correct first order correction to this zeroth order approximation? Okay, so now let's go ahead and solve this equation to first order. So at first order we get the following equation. We get del 2 xa1 by del 2 lambda squared plus gamma abc del xa0 by del lambda del xb0 by del lambda. Okay, is equal to 0. Okay, now this is just so that's d2 x1a by d2 lambda squared is equal to minus gamma abc times y a yb yc. Okay? And we can integrate this equation. Now, let's say that we've set x0 to go between the points that we want. Then x1 has to be 0 at the early time. Lambda equals 1 at 0, lambda equals 0, and 0 at lambda equals 1. You know what I mean? I'm solving this path and perturbation theory, and I've already met my boundary conditions. Namely, x at 0 is 0, and x at 1 is ya. I've already met that with the 0th order solution. Okay? So all the perturbations, x1 at 0 will be equal to 0, and x1 at lambda will be equal to 0, and so on. That will be true at everything. Okay? So now let's solve this. So we want the solution to this equation that has x1 at so anyway, the most general solution to this equation is x1a is equal to a constant ca plus ba times lambda. Okay. Plus this minus gamma abc yb yc lambda squared by 2. This is the particular solution to this differential equation, and this is the homogeneous solution. Okay? And the fact that x1 at 0 has to be 0 tells us this constant is 0. The fact that x1 at 1 has to be 0 tells us that this constant is this object. So this is plus gamma a b c y b y c y b y c by 2 x. Okay. Okay, so we found the correct geodesic path, the path that goes between 0 and the point y, to first order, to the first non-trivial order, namely the quadratic order in this distance y. And it's clear we could continue this procedure to whatever order we want. And we get some formula which we could easily do. Okay. Any questions or comments on this? Okay. So now the next question is, what is the distance between these 2 points? Let's work out the first correction. Okay. So and this lecture is going to be a little short, so I'm going to be obliged to, there's this colloquium on INO physics that I have to attend. So we're going to have a sharp deadline at 4. Let's see how far. Maybe I should just leave some of these details. Anyway, let's. Okay. So now that we found that xa of lambda is equal to ya lambda plus gamma abc yb yc by 2 lambda minus gamma bc a yb yc by 2 lambda square. Okay, and lambda runs between 0 and 1. Now the next question is, what is the distance between these two points computed to second order in y? That's also, of course, very simple to work out, because the distance is given the square distance. Now, I'm interested in the square. Okay, then let's take the actual distance. Square root of g times well, it is GAB del XA by del lambda del XB by del lambda square root. Okay, integrated lambda equals 0 and between 0 to 1. Okay, so we can now plug in. And so what is dxa by d lambda? So dxa by d lambda is equal to ya plus gamma abc by 2 yb yc minus gamma abc yb yc lambda. Okay, and what is GAB? GAB is equal to delta AB times e to the partial omega. Now omega is evaluated at XA. At XA of lambda. Okay? So in order to get everything right, we will also have to Taylor expand omega. Okay? We have to Taylor expand omega. Now to what order are we working? We know that this distance, we know that we're working to the order that gives you one extra y correction to the leading order. So we have to Taylor expand omega to the first one. Okay? So, this is not terribly sure. It's worth doing. It's very interesting. Once. Okay, so omega of xa of lambda is equal to omega of 0 plus del m omega 0 times xm of lambda, where for xm of lambda we substitute this. And to the approximation which we're working at the moment, we will only need to say ym x lambda. It's the leading order in one. Okay? So we have integral square root of this business with delta. So dxa by d lambda, dxa by d lambda. Okay, times omega naught times e to the power 2 omega naught. That's common, so that's, you just put that out here. So e to the power 2 omega naught times 1 plus del 2 del m omega at 0 y m. Okay, so we want to take that object, plug this thing in here, okay, and do the integral over lambda. Okay. Of course, we're not going to try to do the integral exactly. We'll expand to the right order and do the integral. Okay, so okay, I'll finish. 2-3 more minutes, and this is okay. So what we get, this thing here is e to the power 2 omega naught. This part of the square root we can just expand out to the leading order. So that's 1 plus del m omega ym times lambda. Okay, and now this object we want to work out to the two leading order in this one. So the first thing we get is ya plus, let's call this part delta ya. Sorry, that's x naught plus delta x a square root of the 6 square. Okay, so that is the same thing as e to the power 2 omega naught into 1 plus del m omega ym lambda times x naught squared square root into 1 plus delta x a dot x naught a over 2 x naught squared. Thank you. Okay, so now we're almost home, so let's finish it. So somebody's going to have to help me with that. That's formula something. Okay, but let's first formally finish it. Okay, so where are we? So we have first we have the e to the power omega naught times square root of x, square root of y squared. That's a 0th order thing that we have, into 1 plus either this term, the del m omega ym lambda, or this term, plus delta x a dot x naught a over 2 x naught squared is just y squared. Y squared, the square root outside everything. Okay, this was the integral, now we have to integrate it. Okay, so this thing integrates to half because it's got a lambda outside it. And now this delta x a, Jyoti want to help me with delta x a. It is gamma BCA YB YC by 2 lambda minus gamma BC A YB YC by 2 lambda squared. Okay, so we might as well do the integral of this object also. So we do the integral of this object over lambda, and this guy gives us half, this guy gives us 1/3. Half minus 1/3 is 1/6. So we get 1/6 gamma BC A YB YC. Okay? That's what we get from delta x a integrated. We dot this with x naught, which is y a, and then we take this so 1/12 and square root of y a squared. Okay, so we replace this by a half. Okay, so what's the final answer? So our final answer is d is equal to e to the power of omega naught square root of y squared times 1 plus del m omega y am by 2, okay, plus this is gamma ABC, YB YC by 12 YA over 12. Actually, this was not a square, this was over y. Okay, just as a check, this thing, the leading one term is order y, and the subleading terms are both of homogeneity, so that they one order y. Okay, and to completely finish this, I need to know what gamma ABC. So I have to calculate gamma ABC YA YB YC. Just be working as maybe.
Now it's delta AC, del mu omega plus delta C, del mu omega minus delta AC. Okay. This gamma ABC with C raised.
With C raised, fine, but it's all completely symmetrical. We almost dot with y. C. Okay, and now we dot with y, C. Okay, so we get each of these terms is a factor of y squared, and each of the terms is a factor of y dot del omega. It's 2 with the plus, 1 with the minus. So y squared cancels y squared, and we get, so d is equal to e to the power omega naught square root y squared into 1 plus del m omega ym by 2 times plus del m omega ym by 12. Let's check, get the answer. Okay. So this is a very long calculation. I mean, it's a trivial calculation, but we took a long time to do it. But you could have guessed the answer, the form of the answer in symmetric rings. Right? We're going to get e to the power y naught times del n times distance. Then you're going to have the first order, your correction is proportional to y. Okay? If omega was constant, there would be no correction. So it's going to be proportional to derivative of omega, and with symmetric grounds, what else can be brought by something else. Okay, so it's pretty intuitive answer. I have a feeling we messed up on this 12, so we'll know when we get to the final ones. Okay. So even if I mess up on the 12, even if I messed up on the 12, I'll appeal to you people to correct it and get the right answer. You see, the procedure is very straightforward. It's more and more painful as you go to higher and higher orders, as you can see. But this is just to illustrate the procedure. Okay, alright. So, now that we have this distance here, okay, now that we have this distance here, we can now plug this into our formula for what we're going to subtract. Okay. Now you see, the key point is the following. In this distance formula, we're going to take log of this distance. Okay? So log of the distance, this part just doesn't contribute at all. Log of y squared is independent. This part gives us a factor of omega. In this part, when we take log of this term, we're going to expand first order in omega, so just be this term. Okay? So there will be a del m omega times y. Okay? Now, if we were only interested in operators that were evaluated explicitly at y equals 0, then we would set y to 0 and that term would contribute. That was what happened for the attack term. But if our operators have a derivative of x, okay, so that this contraction term acts on that derivative. Okay? Then, that derivative can act on the y, leaving us with a term that's proportional to del m. Is this clear? Okay, so let me make the clear statement. So let's say the things that we will need to calculate are the following. The things that we will need to calculate are the following. We will need to calculate, for instance, derivative with respect to a, y, x, a, etc. Yeah, of the change, the variation of omega of this delta, which was alpha prime by 2 log of d square. Okay? So in this derivative, and this then will be evaluated as y equals 0. This kind of object will be need to calculate. Okay. Now, in this expression here, we're going to get a contribution from two terms. No, actually, just basically from one term here. We're going to get a contribution from this guy expanded. We're going to get a contribution that's proportional to alpha prime, okay, times del m of del a of omega. And of course, if we want to change, the del a of delta. Okay, now in the factor that I'm getting here, it's clearly not going to work. I'm sorry, I'm going to ask you to check these factors more carefully. We're going to get something with some factor. Okay? And Polchinski reports that the right factor is half. So that's clearly not going to work with this 1 by 12. I'm sorry, I messed up badly in this factor. Okay, I'll check this. I'll check this next class. We do nice if one of you check it the next class. Okay, but you see the point, right? You're going to get something. Okay, so I think probably unnecessary. Now you could work this out in one higher order if you wanted second derivatives. And we also need second derivatives. Okay, this I'm not even going to attempt to sketch out in class. I'm just going to quote Policzynski's result. Hopefully what this class has given you is the feeling that you could do it if you want. Okay? And Policzynski's result is that suppose you want del A del B prime of alpha prime by 2 log d squared. This is equal to 1 plus gamma by 2 alpha prime del A del B of delta omega, and del A del B of alpha prime by 2 log d squared is equal to minus gamma by 2 alpha prime del A del B delta omega. Okay, where gamma is equal to minus 2 by 3. And you might think it's funny that somebody would write minus 2 by 3 as, invent a symbol for minus 2 by 3. But the reason that Policzynski's done it is that basically this is the result that you get in the renormalization scheme that we used. Right, I mean this, if you use a different, if distance was not the geodesic distance, something else, you use dimension regularization to define all these things, you get different answers. And the answer will be encapsulated in the change of this gamma. We'll see that. So at the moment, we should just think of gamma as equal to minus 2 by 3, but these answers will turn out to be more genuine as well. Okay, good. So, although I haven't calculated any of these formulas for you since we get that factor, right? What I hope this class has convinced you is that it's easy to do. Okay? So, this geodesic distance is some simple function of the coordinate distance omega and so on. Okay? And in particular, it's easy to determine the variation of this Green's function, the thing that appears in the subtraction formula for operators, with respect to the variation of y factor. If you want up to 2 derivative terms, you have to go 2 orders higher than the naive answer. In class we get 1 order higher, but you have to go 1 further. Interesting. Okay? Any questions or comments about this before we talk? Okay, we're not going to be able to continue long. Okay. Questions or comments? Okay. So now what are we going to do with this? Why were we interested in these formulas? You see, now what we're going to do is take this Polyakov approach to one higher. We don't count the worldsheet tachyon, square root g times tachyon integral. And that seems like an obvious thing to write. But now suppose we go to one higher order in space in worldsheet derivatives. We want a diffeomorphism in variant quantities. We can't have one worldsheet derivative. We must have 2. With 2 worldsheet derivatives, what could we have? We could have e to the pi k dot x, will always take that space dependence, operator, times GAB del AX del BX plus BAB del AX del BX plus phi times worldsheet terms. I've just written down the most exhaustive set of terms that the diffeomorphism invariant, and there are 2 derivative. You might ask, why not del square of x? Why didn't I write a term that is del square of x? And the answer, of course, is that del square of x is 0, or almost 0. We see the right version of that statement inside the path integral. So there's no point in putting an operator that's 0 inside the path integral. It's a path integral. So this is the most general thing you could write down, that is diffeomorphism invariant, and add 2 derivatives. Okay? So if we were following the Polyakov approach, we would, at the next order we will modify this as we put a square root g and integrate over the sheet. Okay? And then the question we will ask ourselves is, where is this insertion while doing it? Now, each of these operators is defined with the normal ordering that we talked about. Okay? So explicitly, each of these operators involves subtractions. Now let's look at the operator that's equal to I, kx, del ax, del bx. The one that comes from, let's say, g. There are three kinds of subtractions here. The subtractions when you're subtracting these two guys. That will work exactly like the calculus. Then there are also subtractions when you subtract one of this, contracted to one of this. That will involve one derivative. If we want to understand how that varies under Y transformations, we want to know one derivative of the variation under Y transformations of this property. Because you see, we have one derivative. And finally, you also have the subtraction involving this guy contracted with this guy. That will involve two derivatives of variations under Y transformations. Okay? So if we know all these three formulas, which we now know, we can very simply write down how that object varies under Y transformations. Okay? Because I have to go to this colloquium, I'm not going to try to write down I'm not going to try to do this now, but could you try this as an exercise? Can you try this as an exercise to write down the Y variation of this object using these formulas? Okay? Using these formulas, please write down the Y variation of that object. Okay? We'll take it from the next class. I'll quickly sketch the answer there, and we'll take it from the next class. Basically, we want to set that object to 0. Okay? And that will be the thing that gives us the condition for acceptable vertex operators. Okay. So, just to remind you, this Friday we will not have a class, and next Wednesday we won't have a class, but we will have a class next Friday. And let's actually, just before going to the colloquium, let's actually set a date for this examination. Does somebody know what, I think 23rd is a Sunday. 23rd is a Sunday, 24th, 25th, 26th, 27th, 28th. Okay, on the 29th I need to down. So we'd like the exam and the grading and whatever grading we do, we'd like the exam discussion of the exam to happen before then. So I suggest the following. I suggest the following. I suggest that we have. I think it's fun. Okay, so what we've done will be basically the final class before our exam will be next week. Then after that, I'm away for a week, and then we have 2 more classes, which are on Wednesday and Friday. I think that's something like the
Friday was
28th, yes, 26th and 28th. But I suggest that we have the exam on the 26th and discuss it on the 28th. Okay? And then whatever leftover material we'll continue in the semester subsequent to that, we'll do that very quickly. We want to rush. Okay, yeah, so let's, okay, so I'll certainly finish Polchinski's discussion of this stuff. Next class, my discussion of the dimensional regularization way of doing it will have to be. Okay, good. So let's fix that's the schedule. So now one quick discussion. Okay, we have to go with one quick discussion about the class or the exam. Maybe